Oh, we're set. Yeah, see if you can find Rob and Alex. They're the speaker liaisons for this talk.
Oh, really?
Yes. So, should I introduce the speaker liaison? What's the...
Introduce yourself.
So, I'm the speaker liaison. I'll be introducing Rob Bird, myself, and Alexander Shagla McKotch here. We're doing the Intro to Data Science for Security talk today. Hopefully you're all in the right place. Okay. Come on in, sit down. Okay. So, just to begin, who are we? Oh, here we go. Who are we? I'm Rob Bird. I work at Akamai. I lead big data architecture for our platform team and the deep learning research group there. We analyze about half the internet's traffic every day, and it's a lot of traffic. Alex is...
I'm Alex McKotch. I work at Rapid7. I'm on the global services team. I'm Alex Shagla McKotch. I work at Rapid7. I'm on the global services team.
So here's a kind of standard disclaimer. I am not Akamai, and Alex is not at Rapid7. We do not speak on their behalf. We didn't harm any marketing people in the making of this presentation, and nobody approved the message, so if you complain to my boss, he won't care, I promise. So our agenda today is going to be pretty straightforward. We're going to take you through a background, like a historic background, on data science, some of its definition and process, and what it usually means for security applications. Then we'll get you up to speed basically on a bunch of methods and talk through some of the background lingo that you'll just have to know. So if you get into data science, if you've never done data science before, this is your first time ever even considering it, you will have to know some terminology, just like you have to know terminology for security. It's the same kind of thing. But hopefully we will not drop our microphones here. And then finally we'll start looking at some data and apply some of these methods. We'll apply it to all kinds of different data just to try and keep it diverse and interesting for everybody. So with that, I'm going to hand it off to Alex, and he's going to start off with our background.
All right, so let's get started. Many people think that data science is something that's very new. It's actually quite old. It started about 200 years ago, probably. Right now, we just use it to define interesting parts of most new applications, and a lot of research has driven the new advancements in data science. Probably the first data scientist was Gauss. When he was a teenager, he created least squares, which was pretty awesome because I believe he was only 16 years old. In 1960, Noir first coined the term data science interchangeably with computer science. And then in 2008, the first person to get the actual title of a data scientist was DJ Patil at LinkedIn. Someone else at Facebook also claims around the same time that he coined the term as well for a job position, but we're going to go with DJ in this particular instance. So what is data science? It's mainly statistics. So statistics give us many of the most powerful tools in data science.
Hey, use the mic. You may need to use the mic.
What?
I think you need to use the mic because I can't hear you.
Can you hear me now?
Yeah.
Okay. Statistics give us the most powerful tools in data science. The most important of which is uncertainty. The next part of data science is math. It's one of the main tools as well. Looking at linear algebra, topology, graph theory, combinatorics. Basically, mathematics is at the center of just about anything to do with computer science, which segues us into computer science. The foundation, a lot of it comes from Shannon's information theory. Lots of methods in data science have close relations to this. And most data scientists are, at the end of the day, programmers. Before, it was all done on pencil, paper, and lots of theory. Now that we have computers, we can compute these algorithms and optimize them and make them faster and more usable using Python and R. A large part of data science is machine learning. provides many tools of data science. In particular, machine learning is used to infer models for using optimization. And this isn't really just optimization for speed, it's optimization for different parts of the algorithm and whatnot. It brings us to visualization and having to do it responsibly. We'll get to that in the next slide. It's a big role in data science because it's very difficult to look at a graph of 100,000 nodes. You want to be able to intelligently display the information so that someone can actually look at it and interpret it. Because we're all visual, most people are visual learners and wanting to see this. If you have a bunch of numbers, it's kind of difficult to take in and grasp that. And this is a good example of data science where it's
not very responsible.
Yeah, it's not very responsible. So this is showing farts and big data and how they are converging. And yes, of course, it is a marketing buzzword now, but the main takeaway should be that it really should be, data science should be used to actually showcase value in your data. Right now there's tons of data created daily, and we need to come up with different ways and better methods to actually consume that data and show its value. So it's just not taking up tons of disks somewhere in a data center.
Yeah, and just to add to that, in security, we often, a lot of people say we have a hard time kind of conveying the value of what we do. It's difficult to convey that to supervisors and so forth, especially if you're not actively under an attack or some terrible breach has occurred. Now, obviously, we can always point to external things, but the great thing about data science is it gives you lots of ways to sort of give you difficult to argue positions for this stuff. So.
The next, one of the key things that you need to have with data science is lots of patience. You must be willing to tune your data models, to clean your data sets with pre-processing. You must not be able to rush to conclusions. If you start looking at something and it looks obvious, then you're probably doing it wrong, or it's for something that is a very standard model or is defined somewhere. Which brings us into the fool's errand. You do not want to get caught in this. So if a pattern occurs randomly in time, even ones that are inconvenient or too good to be true, remember the first rule of data science should be to understand your uncertainty, not your certainty. So if you're looking at something that's very well defined, data science is probably not going to be a good choice for that. Or if you're looking at something and a pattern pops out and you go down that path, you should probably broaden your scope of that and look at the other different methods for looking at it. Or you're just going to go down a rabbit hole and it's not going to be good. And then really data science is more of a mindset than anything else. And it's a mindset of the process. So a simple definition is find things you don't know about and communicate their value. So really data science boils down to you want to think about the data that you're going to be trying to ingest. You're going to think of the process that you're going to want to use to analyze that data. And then you're also going to want to see what the outcome is going to be and put it into a format that others can consume that might not be data scientists or someone that has statistics background or machine learning background. In security, it often means knowing what usually happens. You wanted to look at your data sets and think, okay, if I'm looking at logs, I know that the logs are going to be doing things for syslog, let's say. There should be these kernel messages and things like that. NetFlow, they have a structured format. You're going to want to be able to understand the actual data that you're analyzing. If someone just gives you random data and tells you to do analytics or statistics on it, it's going to be kind of difficult for you to do that. You're going to want to actually read up on the actual data that you're going to be trying to process. And finding the things that shouldn't happen. Looking at the outliers, basically. We're winning, right? This is very easy. Right? No, it's not going to be. And Rob will take that. Are there any questions so far? All right. So, Rob?
Yeah. Okay, so here we're going to get our hands dirty and kind of, for all that kind of overview, we all know math, statistics, that's all part of it. But as Alex points out, it's sort of deceptively simple in security. And that problem of understanding what usually happens and understanding what's unusual and when it happens is a little trickier than it sounds. And we'll talk about some of the things that make security a little more difficult than other forms of data science. Probably the first thing is that we have complicated data types in security. So We've got PCAPs, which are in the data science field, they'll call those semi-structured data. So there's some structure, you have fields, but then you've got other fields that are basically just like payload that are just wide open. Anything could conceivably be in there. We have high dimensionality to our data, so we're dealing with a lot of plain text, we're dealing with a lot of measurements, we're dealing with a lot of potential systems and sources. So if you imagine, for example, you wanted to create an interaction graph that shows all the different source IP addresses and all the different destination IP addresses for a large network and who talks to who. That's actually pretty large. Now, if you try and embed that or send that data into like a neural network or some kind of machine learning model, you actually have to convert that into a form that it can digest. It can't digest tuples like that. So when you end up doing that, you create this kind of binary state space explosion, and it can get very complicated very quickly. And the models that you can apply rapidly disappear, basically, or that are useful. It's highly dynamic data, which for statisticians basically means everything is changing over time. So the means are changing over time is probably the simplest way of thinking about this. And if you imagine a time series chart that's going up over time, where the price just, say the price for a stock, it's just going up, going up, going up, going up, that if you take a slice of that at different periods in time, the mean is changing. And actually the number of methods that can be applied to dynamic systems like that is much smaller compared to the ones that can be applied to so-called static data. And there's some tricks for converting dynamic stuff to static stuff and so forth. And we'll get into all that later on. The next thing is that it's highly stochastic data. There's lots of randomness in our data, timings, everything. We have failing devices, failing sensors, the ordering of packets coming into a queue somewhere. All of these things combine to make the problem a little tricky. So if you imagine you're doing, say, sequence analysis on events, if you're looking at, say, the timings between different events, those can vary dramatically. So it's not as simple as, say, trying to model it with white noise or trying to model it with uniform distribution. You have to really pay attention to the randomness in your data. And actually, for a lot of detailed security problems, this can be one of the most challenging things, actually. It's called state space modeling. And they have a relatively short value window. So obviously there's a lot of value in forensic analysis. There's lots of things that you can do 3 months later after you've detected the breach and someone's complained and your stock price has plummeted. But if you think about actually reacting in an incident response way, real-time data science is a hard problem. And it's a very computationally expensive problem, potentially. And so, again, for security, these things kind of all add up to make our job a little more difficult than the practice examples that you'll frequently run across in data science textbooks. In fact, I was at a large data science conference, and one of the guys said that the hardest thing in data science is finding those magical data sets that seem to show up only in classes, because they don't exist anywhere in the real world. And as far as I know, no one's ever actually analyzed irises and stuff, which is a bit of a data science joke. So the first thing here is when the data is obvious, and maybe this is super obvious, but when the data is obvious and you have a model for it, just use the model. Don't apply data science tools to well-defined things. If you have a protocol that works in a certain way, and you know that the protocol is either broken or being manipulated if it's working in a different way, just define it like that. So there's a lot of this kind of blacklist, whitelist sort of rule stuff out there. And, a good example of this is relativistic mechanics. We know that relativistic mechanics works within our frame of reference in the universe, and therefore, basically if something shows up that's completely violating, say, the speed of light, we know that's really weird and we should look into it. We don't need to train a neural network to figure that out, okay? So take advantage of the tools at your disposal, especially with complicated problems. A good example of this is I was analyzing video content recently, trying to determine quality of experience. And one of the tricks with that was, you have to have different frame rates for different kinds of content. So sports content, you need really high frame rate. A talking head like me, 5 frames a second is really all you need for maximum quality. And I started looking at data, and I was seeing video that was being done at 500,000 frames a second. It's probably reasonable to assume that that's a problem, like a bad measurement or an error or something, right? So I don't need to use an anomaly detector to go through and do that analysis. I could still find it, but it was much easier to just say that's irrelevant. And you'll run into this. You'll run into bad measurements. Just by show of hands, who in the room's ever worked with NetFlow before? Oh, that's awesome. Okay. How many of you have ever seen weird things in NetFlow that make no sense whatsoever? That should be about the same number of hands. Okay, good. Okay. Okay. I would say that the first rule of data science is talk about the process every single time. And I say this because it's really easy to get sucked into shortcuts, and I've done this before, and I'm not going to make that mistake. But especially when you're first starting, just follow a process. And the process is so straightforward and obvious that it's actually the one that you would follow anyway, but just formalizing it helps because you'll remind yourself not to forget parts of it. So sort of the popular data science process, generally speaking, is you have a bunch of data. At least I found this is how a lot of folks tend to think about it. You have a bunch of data, and of course you've got a nice big Hadoop cluster somewhere because somebody spent money on it. And so now you're just going to make money. You're just going to win automatically. There's nothing else to be done really. Once it's in Hadoop, it's done. And obviously, if you're a programmer, you should just figure this all out for yourself. Right? So we bought you the cluster. Why do I not have? I went to a conference. I heard that there were gold nuggets in my data. Why don't you have nuggets for me yet? Right? This is kind of what people will say to you. These also tend to be the people that say things like, "I've got MongoDB, and obviously we're doing great." Just a little to MongoDB there. But the reality is that data science is not your database. Okay, it's part of the data science process, structuring and storing your data, how you access it, and more importantly for data science, the kinds of things you can get the database to do for you can be really valuable. So for example, we're all used to sort of traditional transactional databases that have kind of a row-oriented store. Have any of you ever worked with a column-oriented database before? Some of you? Okay. So column-oriented databases, all they really do is, if you think about how you do analytics, you may have a column that's, say, bandwidth use, right? So if you pre-index on that column, and you represent the data literally as a column on disk, when you're actually doing your analysis, everything will be very fast for bandwidth use, right? So column-oriented databases, array databases, which represent all your data as big arrays and let you do operations in parallel like that. Those are some of the nice tools that shortcut the scaling problem for data science, but they are not data science tools, okay, in their own right. So the process itself is called CRISP-DM, which I think is actually, I don't know, it's a much cooler name than the actual process name, which is a cross-industry standard process for data mining, okay? Just ignore that. The point is it's a very straightforward process that I think, frankly, it's what you'd be doing anyway. What it really says is you want to combine the knowledge and information from your business side, so understanding what value problems you're trying to solve, with the technical knowledge of your data. And quite frankly, one of the biggest problems usually, like in sort of what I would call anonymous or drive-by data science, where you just get some data set off a website for something and you're trying to analyze it, is you're not an expert in that data at all, right? For security data, you are experts in that data. So you've looked at packets. You know strange things are going to show up in there. In fact, they should show up if you're finding weird, if you're finding malicious behavior, right? You have a good understanding of values that you should anticipate. So timeouts, retries, the general flow of protocols, those things are sort of familiar to you, even at like an instinctual level, just from looking at this data for so long. That domain experience is really hard to capture in most generic data science problems. So you're already off, you already have a head start. Okay, we'll see later on why this is very important. The second step is to kind of clean up and, as I would say, like spruce up the data, right? You want to take this ugly data, this raw data that you've collected, and you need to probably reformat it. You need to break it up into different pieces, like say, for example, a payload, like packet payloads. You can't probably just take the raw text content of the payload and just analyze it. You're going to have to probably drop out stuff that doesn't matter, maybe remove random strings, maybe you run regexes to pull out certain key values that you know are inside of a certain protocol. This is all part of the structuring and kind of setup process to your data. And I realize this is not the sexy part of data science, but the reality is if you want to be a data scientist, you will be doing this all the time, and you will like it. And if you don't, get out of this room. I'm telling you, for your own goodness. And he's leaving right now for this very reason. Cannot stand pre-processing. That guy's not into it. Third, you're going to model your data. You're going to come up with reasonable models that seem to fit the data, and you're going to apply them. You're going to formulate a hypothesis, and you're going to try and validate the hypothesis, okay? And I say, I'm being a little pedantic by saying you have to formulate a hypothesis, but don't forget that you need to do that. As Alex pointed out earlier, there's patterns in every form of data. If you just take random binary strings, God, there's so many patterns in there. Oh my goodness, it could be, who knows what's in, it could also just be random binary strings, okay? So having a good model understanding like exactly what you're doing here, understanding that you can't data dredge, which is a process for just throwing algorithms blindly at things and hoping that results come out, is a very important thing. Now, some people say, well, I've very successfully used something like that data dredging technique to explore data. You'll hear it called exploratory data analysis. They're not exactly the same thing. And the reason why I say that is that people that are doing, and maybe even you, when you're doing exploratory data analysis like this, you're really doing it more as an ensemble. Okay, so this is more of a technical term, and we'll talk about it later, but when you run many, many different models blindly against data, it can be done validly, but it's got to be applied in such a way that you're accumulating belief. You're accumulating evidence for your eventual hypothesis that you think that you're formulating. But trust me, having screwed this up many times, get a formal hypothesis, write it down on a piece of paper, write it on the wall of your shower, okay, at some point. Just get it down as early into the process as you can so you don't forget what the heck you were looking for to begin with later on when you think you find something cool over here in the corner. You think you find something cool over in the corner, like Alex, for example? Come back to it later, okay? And we will come back to Alex in a minute. Okay, so in reality, what does the process actually look like? This is what most people think it's going to look like. They are going to just take their awesome knowledge, they just know so much. Man, I've been doing security for 20 years. I am so elite, you have no idea. I go to the 303 party. It's awesome. I'm going to take all that. I'm going to go squeeze the knowledge out of my boss and make him tell me the valuable questions you need answers to, and I will go get you those answers. And then they're just going to, they're going to do a little modeling or a little cleanup, and then it's just going to be all about the modeling, man. We're going to use neural networks. We're going to use, genetic optimization. We're going to do all these cool things you never even heard of before, and they sound so impressive. They will raise VC money faster than you've ever seen. Okay. And then eventually you're going to figure out how you actually evaluate if it was good or not. But you know what? That deep neural network you used is so cool. There's part of a problem here with this is that, really in the common literature right now, modeling is the sexy thing, okay? It is so hot right now. Which, by the way, ironic scene. In this scene, he's actually saying that Hansel is so hot right now, and Hansel is right behind him in the upper right corner. For anyone that sees the movie, is a bit of a trivia buff. So in reality, this is what the model really looks like, okay? It's very hard to find domain knowledge. It is very hard to get business insight on the questions that they're looking for, aside from why I want valuable answers. Well, don't we all? Okay. But the question is, do you have valuable questions? And there's a lot of data science done without this focus, and I think it kind of discredits the whole effort, because really all you end up saying is we found all this stuff and we have no idea what it's for and if you're going to care or not, but we did a lot of algorithms. The reality also is you're going to do a ton of data cleanup. This is very painful, okay? Think of something like IP addresses. On the surface, an IP address sounds like a very simple data point. I've got a column, it's got the IP address. Now, what if you want to gauge the similarity between two IP addresses, okay? There's a lot of ways you can answer that question. So you could say, okay, well, maybe it's just the last octet. Maybe I run a trace route between those two IP addresses, and I determine the number of hops. Maybe I have a BGP network map, and I use that to help identify, maybe some notion of proximity or similarity. The point is, there's a lot of ways to skin that cat, and it depends on what you're trying to find out from the IP addresses, how you present them to the algorithms. Because the algorithms aren't going to solve this problem for you. The modeling algorithms don't know what an IP address is and don't care. They expect you to care and to figure out what they mean. Otherwise, they will make you look like a jackass. And I promise you this, you can draw bad conclusions. It's very, very simple to do. Like I've seen people use IP addresses in their integer form and plug them into a regression algorithm. And all it's really telling you is what's the ordering of the IP addresses in integer form. It's literally useless to you from the perspective of identifying unique endpoints. Yeah. Yeah. Yes. Converting it to a 32-bit number. Yeah. Yeah. Not destroying data, but again, also in that case, you're actually presenting it to the modeling system as an ordinal, like a form of rank data. And it's not, right? And you are destroying data in the sense that, well, you're not exactly, but it's not what a typical integer value might be, right? So a typical regression algorithm might look at that integer value, or is expecting to see it as something like a bandwidth counter, right? Not a graph structure over, a global graph structure basically over a hierarchy of data where you've got really leaf indicators on a tree, which is a totally different kind of data than just numbers. You have a question in the back, yeah. No, you're sort of doing it the opposite way. You're sort of, the way I would describe it as, and that's a good question because it's the reality of data science, is you're biasing the search. I'll state our big secret. You're biasing the search in ways that you know are meaningful, and this is part of the apply the human knowledge component here. I recently came across a really clever idea for how to vectorize IP addresses, how to turn IP addresses into a form that I could use them to calculate, neighbors and find clusters and those kinds of things in terms of activity. And it was a brilliant idea. It was a brilliant idea. And literally, over the course of the last 15 years, I've looked for ways to vectorize IP addresses. There's probably 2 or 3 papers on it, total, in all of academic literature. It gives you a sense that this is part of that weird data from security. People just go, oh, it's just IP addresses, whatever. They're categories. I'll treat them as unique, hash values or whatever. But that's destroying data. And a security person knows that's destroying data. And we know we can take advantage of that. The question is how. So presenting it in a form useful to the algorithm is critical. And then finally, it's measuring success. Measuring success is hard in security. It's obvious for things like, well, it's an attack or it's not an attack, like classification problems, okay? But it's not obvious for things like good and bad. Right? What one person might think is good, the other person might think is bad. A great example of this, since I was on this side of the fight for a while, is detecting illegal P2P activity. Okay? So imagine the classification problem of analyzing P2P network traffic, determining if it's, quote, illegal copyright violating behavior or legitimate behavior. Now assume that the P2P network is encrypted. How exactly are you going to make that conclusion? Right? You can't. It's very difficult to make that conclusion unless you kind of insert yourself in the path and do a bunch of other tricks. And even then, you're not really making any kind of judgment whatsoever. Like you can't determine, for example, is this person using it with fair use? Is this Britney Spears downloading her own music and distributing it from her dorm room? That's literally possible. When I was at the University of Florida, we actually had a famous singer living in the dorm who we busted for distributing her own music over a P2P network. Okay? Funny story, but true. Okay, so any questions on this stuff before we get into some of the lingo background goodness? Okay, so I'll let Alex pick up here.
All right, so next we're going to get into some of the lingo. We've kind of touched on
raise that up still. You're still really low. Yeah.
That's as high as it goes. Gonna get a nice wide stance. Oh, yeah, that would work too.
All right.
Well, it's not as long, but it will work. All right. All right, so we kind of touched on some of the lingo while we've been going over this. Now we're going to add some formal definitions to it. So first we're going to look at some data types. Really for our purpose here, we'll be covering 3 main data types that are about 90% of what will be covered in security. And each one of them will have to be pre-processed and modeled.
Yeah, one thing to note on the different data types too is that if you can't put your data into one of these 3 forms, you may not be looking hard enough. And if you really can't put it in one of these 3 forms, talk to me because I want to hear what it is.
Yeah. Okay. All right, so the first data type, we're looking at categorical data. These are represented by counts or binary existence, like bags or sets, anything that you can put a real category to. Next is ordinal data, so this is a ranked data. So like in our example, we have the different metals, and we know it's different ranked based upon the color of it. This is based upon equal spacing.
Yeah, the important thing to also imply here is that it's not the same thing as just putting integers as 1, 2, 3. Okay?
Correct.
So the subtlety here is that gold is not 1 unit better than silver, which is 2 units, which is 1 unit better than bronze. Gold is 100 units better than silver. Silver is maybe 10 units better than bronze, so on. So the algorithms that handle ordinal data, which again, it's a very small subset of algorithms that actually deal with this nicely, will let you tune kind of relative values and weights and how to deal with ties and things like that.
And then finally, numerical data. This is very easy. We see this all the time. It doesn't really take a lot of pre-processing, and it's usually very direct data. Lots of numbers. So it's pretty easy to look at. In a spreadsheet, you just have the numbers and you'd have the values associated with them, where you wouldn't really have to put much weighting on it or anything like that. This is probably the simplest data set or data type to actually work with, is just numerical data.
Yeah, nice continuous numeric real numbers are gold.
All right, and we've touched on this before with the pre-processing. So this is probably the actual hardest problem. So we have all these equations and whatnot we can plug data into, and then the main thing that you have to do is actually sanitize your data and pre-process it. So these things will be looking at time series and normalizing the time, normalizing your actual data itself, trying to just make it so that it can be ingested by these models and algorithms. If you have a spreadsheet, let's say, 50 different topics, and most of them are blank spaces in there, it will throw off your model. So you'd want to extract the data that you want to use for the specific use case that you're going for. If you're looking at logs, for instance, you might not care about like warning or observed or the different types of severities. You just want to know what the messages are in terms of time. So you don't need that extra data involved, because it can just change what your model will look like at the end. So this is really where you're going to spend most of your time. It's very good too for when you're trying to train your algorithms or compute your fitness functions. You're going to want nice data. You're not going to want to have lots of sporadic jumps or leaps in your data, or have different pieces missing from your data. So how do we really do this? Most numeric types of data, we can compute a z-score. So basically you're looking for a variance mean of 0. For time, you're going to want to normalize the time. And what you want to do for this is figure out what outliers could exist. So if something is like 6, like the z-score is like 6 derivations away from the mean, you're going to have something that's really going to throw off your model. So you want to look and see why that is beforehand, and then try to correct that in your actual model. So the best way to do this, to normalize it, is by using a z-score, which is pretty standard statistics. Yep.
Sigma, yeah.
Yeah,
Sigma. So mu is the mean, and sigma is the standard deviation of your data.
So if you looked at a bell curve, you're basically computing the z-scores for each of the different deviations off of each side in respect to the mean.
Yeah, the key net result here is that after you z-score numeric data, the mean of that data is going to be 0, or at least extremely close to 0. And the variance for that data, as well as the standard deviation, will be 1. So you should have unit, standard deviation, and mean. The other half of the normalization equation for numeric data is getting them on the same scale, or getting them onto an equivalent scale. So for example, if you've got data that goes from, say, 0 to 2 to the 32 in one column, and data that goes from 0 to 1 in another column, when you actually, if you just plug those as raw numbers into linear regression algorithms, as an example, the scale of the one that goes from 0 to 2 to the 32 will dramatically dominate the data from the 0 to 1 scale. So you have to put them on the same scale, basically, to kind of put them on equal footing, to give them equal space in the data space. So.
All right, now text is kind of a special case, because text can be encoded. Look at like a packet, for instance. If you look at the data portion of the packet, it's usually encoded. You don't have like the raw information there. So you're going to have to pre-process packets, especially a lot, and text in general. And different things can be encoded into it if there's something, if you're looking at a covert data channel or whatnot, like someone did another talk, where different parts mean different things in the actual string itself. You can add context to these things. There's a couple different ways to do this. If you look at the sliding window, basically, like kind of Google does for searches, is a sliding window that creates n-grams. So it's basically moving across the text to find out these weighted words, basically.
Yeah, basically text sequences like DNA, they're all encoded, even numeric time series, they're encoded over windows usually, or they use specific models that take one data point at a time and predict the next symbol. So the great example of the predict the next symbol one data point at a time is any kind of advanced compressor, like an XZ compressor or like ZPack. They take a single binary value each time and predict the next binary value. The other way, as Alex describes, is that what they call the bag of words or bag of letters, depending upon how you do it. But basically what that's saying is, like for Google, they take what they call 5 grams. So they're sequences of 5 words. And they've actually released a data set that has every sequence of 5 words found in every book on Google Books. And it's like this gigantic 1,000-file data set. But what that tells you then is it gives you, you're basically encoding a model that understands 5-word context. Right? Now it seems like, well, why 5? Why not 3? Well, you can use increasing amount of context to give your data more and more value, maybe give it more relevance. So kind of the basic case would be I just count all the words. I count the instances of the, I count the instances of a, et cetera, et cetera, et cetera. Maybe I remove the very frequent words like the and a, and I just look at sort of the valuable content words. That's going to tell you something about what you're looking at, but it's not going to be able to predict the next word with any real accuracy, and especially when you look at things like human language. The complexity of human language is very high because it's Turing complete. So it needs all kinds of phrase structure and context across sentences and what was I reading in the last paragraph and everything else to really tell it what it's doing. So you can imagine if I tried to build an n-gram model that was 1,000 words long, well, first of all, I've got to have 1,000 words, right? Second of all, I need such an incredibly large amount of data to get counts that are not 1 for every single one of those 1,000-word blocks that it becomes effectively useless, right? Everything becomes random again. So text is really tricky. Sequences are really tricky in general. Time series are really tricky in general. There's some good... our goal today is to kind of show you the methods that won't trip your feet up and can be practically used quickly. Okay, so...
And like Markov chains kind of use this, this factor of n-grams to kind of predict the next word that's going to be did for sentence generation and whatnot. There's lots of stuff on that online. The next kind of data is graphs. These can be encoded graphs, binary trees. Different input models will give you different graphs. Low-dimensional embeddings can be used to fix the dimensionality. So if you have a very large, sparse graph, you'd probably want to encode different parts of that for it, depending on your model. So this goes back to the kind of the pre-processing and whatnot.
Yeah, to kind of lay it down, like if you take the Facebook social graph, right? And just imagine that we're going to create a giant matrix of zeros and ones. You have a 1 if you're connected to somebody, for that row and column. You have a 0 if you're not connected to that person. Okay, so if I want to, quote, analyze your predictions or your connections, I can imagine I've got this enormous row that's you. It's probably, 990 million zeros and then, a couple of ones, like maybe a few hundred ones in there. That's a very sparse matrix. The matrix of all of the users of Facebook is very sparse. Of course, the problem there is, look how big the input vector is. You've got a, 990 million length long array for each user. And so if you're calculating values and probabilities over all these different values, it becomes very difficult to do. So what you can do is there are techniques that take a giant high-dimensional thing like that, like each row, and compress it down to like a fixed number of rows, like 64, columns, like 64 columns or 256 columns. So those are the low-dimensional embeddings that he's talking about. And there's some great algorithms in scikit-learn for doing this kind of low-dimensional projection. And we're going to talk mainly about Python tools today, but there's tons of tools that will do this for you. Don't mess around with it, and please don't try and plug those raw rows into your prediction algorithm. You'll kick yourself for how long it takes. So
yeah, it will blow them up, especially if you're using MATLAB.
Yeah, don't use MATLAB.
Use R or Python.
Yeah, just use Python.
And then the next thing is missing data is one of the more difficult things as well with the pre-processing portion of your analysis. It is important that it should be noted that all the models can cope with missing data in most cases, that it won't really throw them off unless there's huge gaps in the data. And solutions for this can be adding in very noisy data into it. You think that wouldn't really work, but injecting very noisy data into the normalized data can fill in those gaps for you. So if you look at like signal analysis and you have a missing the frequency dropped or whatnot, or you just have a chunk of it gone, you could take something that is very similar to it and inject the noise into it, and then you can compute how that would fill in those different parts of the data.
Yeah, so for when we said earlier that like continuous numeric data is easy, it's easy for a reason, because we can use interpolation techniques. So, for example, if you've got, at 2 o'clock in the morning, you have a measurement of the number of B-sides attendees down in the casino. At 3 o'clock, you don't have a measurement because somebody got drunk and forgot to write it down. 4 o'clock, you have one. You can interpolate between the two values and kind of estimate with a linear model, what was probably at 3, and then you can plug all that into the prediction algorithms. The main thing is that actually, without doing this stuff, I'm going to contradict Alex. Most models cannot work with missing data. They will fail. So there are a few models that kind of handle it for you under the hood nicely, but I guarantee you all they're doing is exactly the same techniques you would apply manually. So what you really want to do is find data that's not missing a bunch of values, okay? Try and get good measurements. This kind of speaks to the core problem too. Like oftentimes with security data, you'll get in there and you're like, we've been archiving data for years. And you decide, okay, I went to this data science class, I'm going to go try some of it now. You get in there and try it and you realize, uh-oh, it's not measured at equal time steps. It's measured whenever the measurement was taken, and there's missing data all over the place, and that file got deleted 3 months ago, and whatever. It becomes very tricky. Now, if you have a giant gap, as Alex said, in your data set, interpolation probably can't help you. It's probably more valuable to throw that data out entirely. So like if you're missing, if you're measuring bandwidth usage every month, or say like every minute, and you're missing an entire month in your model, throw the month out. Don't try and interpolate the month, because you're missing too many points to give a meaningful interpolation.
And especially with like logs too, that you can see this, like if an attacker comes in and wipes your logs, you can't really look at that and try to model that. So you're just going to have to look at the data and see probably what the best method would be to actually be able to create the models. All right, next part we're going to go over is data sets. So the first part is pretty much independent on time. So if you look at a spreadsheet, for instance, if you don't have time in that, it's a good example. You do like pivot tables and whatnot. There's no actual time scale to follow for those. So if you have like colors and ice cream, there's no time scale to look at that. Or people's names and what their choices would be. There's no way to actually interject time into that. And then next thing is time series. So there's really two types of time series. There's stationary time and non-stationary or dynamic time. So stationary time, basically, the mean is stable. So if you have something that you're looking at it and the graph just spikes up, or there's like big jumps for like multimodal data, that won't be stationary.
Yeah, I'm coming to give you this mic.
Oh, okay.
So that way.
Oh, great.
Perfect. Can I turn this one off?
Yeah. So you can either hold this right here. I understand that one's on.
This is better. Okay, is this better? Yeah, this is perfect.
Yeah.
All right. So dynamic data is more descriptive statistics are changing over time. The price of a stock index is a good example of this. If you look at the stock data for the last 20 years, you'll see it's very multimodal. There's big.
Just keep going.
That didn't look right. I will not move the microphone like that again. All right. If you Is this okay? Hello? Hello? Is it working? Test. Is this good here? Okay, perfect. Yeah, so we look at the stock market. There's really no way there's no stable mean in that. It's ever changing, and there's dips and spikes. And if we look at something like, there's not ways to predict things like 9/11 or whatnot. There's a huge drop. Unless you look at like a chaos model or whatnot, they can try to predict these things. Is there any questions?
Okay, so misclassified data. More sophisticated classification models are stochastic models. They assume a certain amount of error in the data, which can include the classification. Okay, and there's a lot of different kind of tricks that you can do. So, like as example, if you if you have a certain amount of confidence in each source of data, like say antivirus vendor B, we see misclassifications 1% of the time. Antivirus vendor C, we see 90% misclassification, whatever. You can factor that uncertainty into your model. And granted, you're just estimating it, but it's better than zero, right? So even if 90%, it's 87% or whatever, the point is you're trying to factor some of that in. And we have other techniques, Bayesian methods, which deal with uncertainty just implicitly in numeric data very nicely, and there's some categorical methods as well for that, and ranked, and ordinal data methods as well. Yeah. Yeah. All right, cool. Okay, so this part we're going to talk about analysis, and coincidentally, we're going to start off with analysis of uncertainty. As we mentioned earlier, uncertainty is, in some ways, it's the most important lesson from statistics that we take away. So most people think about statistics, they think about probability, they think about this, but what is probability really telling you? It's giving you a sort of a degree of belief in something as opposed to absolute binary certainty one way or the other. In fact, it's funny, I talked to somebody at work who said he doesn't even believe in binary at all. He's like, it's just an illusion. He's a pure statistician. But the reason why this is so important is because that essentially all real-world data has got uncertainty in it. Right? If you imagine, like an Akamai scale, one of the things that we factor into, we have, 250,000 machines basically scattered around the planet and 10,000 data centers. We look at cosmic ray modification of timings and drop and loss. That's factored into our models because we have to, because the amount of data we see is large enough that it's measurable, right? Network traffic gets dropped all the time. Routers fail. Measurements are bad. Hackers control your devices. They're injecting fake data. All those things factor in. So really what you have to figure out is, one of the core questions in statistics is sort of this idea of, do I have enough samples for what I'm looking at? How do you even know if you have enough samples? Did you really, are the samples you have so far even representative of your data, or are they just a huge burst of outliers, right? Unfortunately, a lot of data science and security tends to get applied in an emergency, almost like in desperation. Like we can quickly try and find something. Oh, I see a spike here. Okay. And you just kind of roll on with it. But that doesn't mean it was actually valid or useful at all. And this is kind of a core conundrum in statistics. Like sometimes people will tell you there's different rules of thumb for this. The general rule of thumb that I use is if you're dealing with univariate data and you plot that data and the distribution of that data appears to be relatively normal or stable, like it looks like a distribution you can draw or look up in Wikipedia, maybe is a better way of putting it, that's pretty well understood data. If you're looking at data and it's high dimensionality, the other rule of thumb is essentially you want to have basically 2 to the dimensionality of your data, or 2 to the number of columns of your data before you consider it an adequate number of samples. Now, why should that be throwing off red flags for you? Because if you think about, say, like the character n-grams that we talked about earlier, like let's say I'm going to take text, I'm going to encode that text as a vector that counts the number of 4 character sequences in that text. Okay, so it's, I've got A, B, C, D once, and then the next thing comes up, and I got 3 of those, and whatever else. Say like the space, I might see a lot. Okay. Question. Okay. The problem is that the dimensionality of that is extremely high, right? So you have 27 to the 4th possible combinations there, and so if you have to get 2 to the 27th to the 4th examples before your data is valid, then you're going to be waiting a long time to get enough data. Okay, so you're oftentimes going to be running in situations where you're just going to have to go with it. And as Alex pointed out, there's some interesting tricks here, which basically involve injecting random versions of the data you already have. So you basically use the data samples you have, you kind of gently perturb them, especially if they're numeric values. You may add, typically it's all additive noise, but you would add, say, a slight deviation to that value. So rather than being, we measured 1,000 bytes from this user, you could turn that into, say, 100 lines of, we measured 100 bytes, we measured 100.6 bytes, we measured 99.1 bytes, right? Even though the 0.1 doesn't mean anything to you, to the algorithm, what you're really doing is you're giving it smooth data, okay? And so when something is trying to learn, it's trying to sort of drive a rover over a complicated landscape, if you will. to find the lowest point in that landscape. If you give it sharp rocks, it's going to blow tires out and get stuck all the time. This happens. It's called getting trapped in a local optima. If you give it smooth data, it can very frequently find that minimum with no problem. So dealing with uncertainty, in a sense, can basically mean injecting uncertainty. And it's a little counterintuitive, but it works in practice. We really have two main tools for dealing with uncertainty in statistics. One is what I would call the maximum entropy rule, if you will, which basically means that all things considered, if you have a bunch of different models for your data, you want to choose the model that maximizes our uncertainty given what we already know. So notice I'm not saying pick the model that maximizes the correctness of what I do know. Okay? Because what you have to assume is that you don't know everything. In fact, you probably really don't know everything, and you're better off picking maximum entropy as your selection point. A great example of this, I think, is the crash here on 9/11, right around the time after 9/11. Quite frankly, there are a lot of mental models and computational models that factored in some measure of uncertainty, right, to different degrees. Some people were completely skeptical of the market. Some people, because they were already questioning it because of the tech bubble. Some people were worried about terrorist attacks, but most people were working within sort of a bound. Very few, if not zero, people predicted the simultaneous occurrences of 9/11 and a major terrorist event in New York City at the same time. Sorry, the tech bubble exploding and 9/11 actually occurring at the same. Wow, those two things are weird. However, it's maybe sobering to know that a maximum entropy selection model would have accounted for those two things. So maybe on the surface, your intuition is to say, well, if I'm accounting for every possible thing that can happen, you're not accounting for it equally, right? You're not saying that a plane crashing into the World Trade Center is equally probable to an ear of corn growing from a corn stalk. You're saying that I'm thinking that all of them can exist and I can assume some type of probability to those events, even if I don't even know what the events are that I'm trying to assign a probability for. So how the heck do we do that? Well, that's where kind of our second tool comes in. This is Thomas Bayes. This is the creator of what's called Bayes' theorem or Bayes' rule. And basically, Bayes' theorem lets you work in your prior knowledge, your prior expectations about the probability of certain events, combine it with the evidence that you're actually gathering, and then make a new prediction based on all that stuff combined. And actually, it's interesting because human beings in kind of blind trial tests do not act in a probabilistic fashion. They tend to act in a Bayes' theorem fashion. So if you think about everything that you've ever learned in the course of your life, and somebody comes up to you and tells you something, it may line up well with your notion of uncertainty, like, oh, that kind of sounds like what I've heard before, so therefore I don't need a lot more evidence. If somebody comes up and tells you something absolutely astonishing, like, hey, I built a car, it's outside in the parking lot, it can drive faster than the speed of light, you're going to want to go see that damn thing, right? And you're going to want to touch it, you're going to look at the motor, you're going to want to see it actually driving faster than the speed of light, you're going to want to sit in the car while it's going faster than the speed of light, right? So basically, the more, it's not saying that uncertain things can't happen, and it's not saying that you have to perfectly predict that uncertain things are going to happen or not. What it is saying is that you can give them all a chance, okay? And that increasing amount of evidence is necessary to confirm your belief when things are really unusual. It's a pretty intuitive notion for humans. It's actually expressed literally in this formula here, which I can't remember the name of the company. They're acquired by HP, if anybody knows. It's like $10 billion. Anyway, this is from their lobby. But basically, the way that this breaks down is A is the prior information. This is what we believe before we start. This is our probability of belief in our hypothesis. B is what we measure, so it's the evidence that we've gained. And basically what it's really saying is just what I expressed before, that basically, sort of informally, if the hypothesis was extremely unlikely, we should also reject it unless we have a lot of evidence for that new hypothesis to kind of completely realign our expectations. Bayesian methods in general in machine learning and optimization or like regression problems tend to represent sort of the gold standard for accommodating uncertainty into your model. And we'll kind of focus on those Bayesian methods because just in experience, they apply very nicely to security problems. Okay, so now we're going to talk about the analysis of data to actually find patterns and anomalies. So as we pointed out earlier, one of the simplest problems in security is knowing what usually happens and finding stuff that probably shouldn't be happening. Okay? So the question is, how do you know that? How do you know what's usually happening? How do you know what's unusual? How do you do that in practice? And this is kind of the part of the talk where I say, as much as security is usually, we sort of think of ourselves as kind of this ivory tower niche where we're special, we know stuff that other people don't, et cetera. In the analytics section of data science, there's nothing special about security except for the complexity. So I'm going to show you some really complex data that's got nothing to do with security, and I could hide the axes and change them out for something else, and it would work exactly the same way for you. Okay? So what is normal? You know, this is kind of an interesting concept, and it's maybe not coincidental that normal is actually a name for something in statistics. So in statistics, we have the normal distribution, this bell curve, which hopefully a lot of people... Has anyone never seen the bell curve before? Okay, thank God. I've had hands go up there. Okay. This is also called the Gaussian distribution. This was named after Gauss, obviously. And, you know, in this sense, in this what we call unimodal sense, we have one kind of dominant value here, or range of values here. Basically, we know what normal is by taking the average. So if we have normally distributed data, and I want to know what, quote, normally happens, the value I would expect to see most of the time, my best estimate of that value, it would be the mean. Okay? And if I want to know what's unusual, well, I'm going to look out here on the tail. Right? So the normal distribution, by having a well-understood formal distribution, tells us exactly how to find normal and unusual. It gives us a rule. We even have percentages for it. Right? That's really convenient. Remember when I said earlier, if we know that something follows a certain model, just use the damn model. Don't go throw tools at it. If you know you have normally distributed data, just use it. You can just use these percentages, calculate your z-score, which, by the way, equate to these values here. So this is 3 z's away from 0, basically. That tells you how unusual your data is. Simple, right? So I can just filter out my unusual data or look for high deviations. Everything is dandy. And what's also interesting is that this is the most common distribution in nature. So a bit of a personal habit, I'm trying to actually determine there's a whole category of distributions that are very stable in nature. They're called the stable distributions. And the normal distribution is one of them. And the fat tail distributions are also part of the stable distributions. And what they call Levy distributions, which are even fatter tails, are also part of the stable distributions. They're all the same. They're all related to each other functionally, like in the equations. This is interesting because actually the sum of arbitrary noise is Gaussian. So if you take, you know, I create Levy noise and Cauchy noise, all these weird noise types, and I throw them all together and I add them up, I'm going to get a distribution of data that's basically normal. So it makes sense that this occurs in nature very frequently because there's all kinds of weird random noise all the time created by different processes. And when you lump them together, you get normally distributed data. And this is very fortunate because it's really easy to work with. We can calculate the mean, we can calculate the standard deviation, we can do that stuff. For other distributions, you can't even calculate the mean. So, and it matters. This is called an attractor also. You may have heard of that from chaos theory, things like that. It's basically an attractor for, like, when I say attractor, when you take different stochastic processes and you tend to combine them together, it will attract to one of these states. So a lot of things in finance are modeled by, not this anymore, but, you know, Cauchy distributions, these fat tail distributions and so forth, for this very reason. Okay, so let's talk about how do we do this for categorical data. Okay, categorical data is arguably the simplest kind of data to do this for because it's already in the exact form you need to analyze it. There's nothing else to do. You just look at the counts and look for the outlier. Okay, so in this photograph, we want to find our outlier, which is probably that iPad right next to the Pope there on behind his shoulder. Basically what I mean by this is if you've got like a bar chart that counts up, you know, the number of TCP packets, the number of UDP packets, et cetera, et cetera, et cetera, and you've got like this one weird DNS TXT packet floating around or 100 of those, you probably want to look at those first. So you can just use the straight counts. They are indicating your probability directly. If you want to be Bayesian about this, you can apply the categorical distribution as your prior, and then apply your evidence, your actual counts here. Okay, this is big D here. Let's talk about one-dimensional data. Okay, and we're going to start with numeric data here, and basically just kind of put it in standard context. Okay, finding patterns in one-dimensional data is typically called histogramming. So if you've seen a probability distribution, it looks like a histogram, a bunch of bins kind of lined up. That's estimating the exact process, that we have, say, for example, this nice continuous thing for. So basically, why is this of any relevance? So if the data is shaped like this, it's easy, right? We know how to find the mean. We know how to find the standard deviation. It's a piece of cake. If the data is not shaped like this, we can't use the mean. This happens all the time. I cannot tell you how many security products that, if you use commercial security tools, find out what the heck those scores mean and how they're calculated in your tool. Oftentimes, they will be assuming that the data is normally distributed, and the data could not be farther from the truth as normally distributed. And in fact, the values that you're getting are literally, they're not just wrong, they're screwing you. Okay? So a good example of this is this data set here. Now, they are the same data set, represented by two different histograms with different bin widths. Right? The one on the left's got a nice big fat bin. The one on the right's got, I think, an equal number of bins to the number of points. So it's about as good as it can be. Just using raw stuff. So obviously, they're totally different. They don't even look the same. There's a huge mode in the center on the right side that's completely gone on the left side. Right? It's kind of blurred into the center bins. Well, that's a challenge, right? How wide do I make the bins? Do they all have to be the same width? How do you even make this decision? And you might say that there's a couple different kind of rules of thumb that people have tried to deal with this, and strangely enough, it has not been solved for quite a while. This was a recently discovered kind of solution to the problem. It turns out to be a very elegant and simple solution, but a solution nonetheless. So here's an example of two different methods. One on the left is called Knuth's rule, not to be confused with Don Knuth. This is like Bob Knuth, who's not related in any way. And he attempts to actually estimate an optimal average bin width. Okay? It's pretty good, but it's not great, mainly because it doesn't incorporate our uncertainty around these measurements at any point. It's just using the straight data as it is. There's no Bayesian anything involved here. The second method is a Bayesian method called Bayesian blocks, and it was developed by Jeff Scargill at NASA. It was specifically used to spot rare measurements in deep space, deep field light measurements with photon sensors. So what he's looking at is he's trying to find really, really far away stars where it may have a sharp transition in that region of space, but because it's so far away, it's just small. So we need something very sensitive that can still pick up a tiny spike without running it over and without blowing up our complexity, right? And we'll talk about in a second why that matters. So one thing that you'll notice if you compare these two is that the kind of fat tail things, like out here, this bin is very wide, right? So it's assuming out here that this is essentially the measurement out here. Of course, in here, the bin width is very narrow. So Bayesian blocks uses adaptive bin widths specifically to create an optimal model. It's a dynamic programming solution, and basically gives us a nice solution to this problem. The key is this is already implemented in a bunch of Python libraries. If you want to histogram a bunch of 1D data, you can either go read the algorithms and understand them, or you can just go apply it and get a great histogram output and just use it. Now, why does it matter? Why can't we just use the guy on the right? Does anyone know? Why would we want to have this guy on the right here, our Bayesian block one, versus this little fine bin width one on the right here? That's one reason, definitely. You don't know how many bins there are going to be. Who knows how many points you're going to end up measuring? Maybe today you got 1 million, maybe tomorrow you got 100 billion. But is that there's something more subtle going on here. There is noise in the measurements, but actually the histogramming should account for that. That's part of what you're trying to do with the histogramming. It should be noted that in 2 dimensions and up, histogramming gets called clustering. So if you've heard clustering before, it sounds a lot sexier than histogramming, but they're the exact same thing. Still not quite there. Any other guesses? Exactly. It does not reduce the complexity. That is the main issue here. Okay. Now think about human beings. Think about Occam's razor. We want the simplest description of the problem that we can come up with, the simplest description of our data that accurately describes the data as accurately as possible. So while the one on the right here works, it's incredibly complex. If I try and calculate the entropy, or say estimate the entropy from these different bin measurements, I'll get a measurement that's essentially very, very close to 1. Okay, so like when you calculate entropy, you're taking a log. The log base, in the case of doing this correctly, needs to be actually the number of bins. So if the number of bins is very large, if I have 100 million as my logarithmic base, it takes incredibly large counts to vary the base. So at the end of the day, your entropy ends up being very, very close to 1, right? It kind of approaches 1. If you use Bayesian blocks, you get a very small number of bins. So even though it's just as descriptive, it's much simpler, and so we would prefer to choose that model. So even if, for example, the entropy measurement of that one versus this one were identical for some quirky reason, you would prefer the Bayesian block measurement because it's simpler. It's a simpler description of the same thing. So if you think about it this way, it's like I can take a program and I can write it entirely in machine language. That's great. But putting it to work, the complexity of that solution is extraordinarily high. I'd prefer to write a program in something like Python. Yeah, it's going to turn into machine language. But in terms of my description of that problem, it's a very efficient way to describe that solution. So this is the sort of mathematical equivalent of the same thing. For the super nerds, we're minimizing our Kolmogorov complexity by doing this, by the way. Okay, so what does this look like for greater than one-dimensional data? Now, it's one thing when you got one-dimensional data, it's pretty easy to come up with bins. But when you move out of 1D, suddenly shape starts to matter. You don't really have shape in 1D. You have regions of density and non-density, really. But higher dimensions, we have different ways of doing this. So here's an example displaying population density of the United States. This is from Wikipedia. 2D data doesn't usually lend itself well to using simple clustering methods. So it does in sort of practice data sets. You can use a grid. You can just break up the entire country into grids, like our bins in one dimension. They'll just be grid squares. And I can count the number of people in each grid square, and I can use that as kind of a raw histogram estimator of my data. But typically speaking, this can yield some pretty ugly, frankly, looking output, and it can be pretty counterintuitive, because what does a grid square mean? I mean, the country is not a square. So how do you map a grid square to the coast of California? It's moving in. You're going to have, do people live offshore? Are there houseboats out there? Like, what are we talking about? Right? There's a typical solution to this, which is called kernel density estimation, which basically takes a big grid square implementation like this and then smooths it. So basically you take if you've ever used like Gaussian smoothing in an image processing, like in Photoshop for adding blur, that is exactly the method applied here. Okay, so you can either take the grid square implementation, smooth the resulting counts using a Gaussian filter, or you can take every point where there is a person. Imagine that you place a Gaussian function, that bell curve, at that point, and then look and see what the intersection of all of those looks like. There's kind of two different ways to get to the same place. So what's wrong with this kind of kernel density estimation? Well, what's wrong with it is that you're making an assumption. The assumption is, what is the shape of my bell curve? So is it a fat bell curve? Is it a really skinny bell curve? And that assumption is hard to make. And why is it hard to make? Let me give you a great example. So this is from Wikipedia. I think this was originally done by NASA. Okay? Here's what Stanford got. This is the exact same data. Okay. Now, the importance here is that it's not that the data was wrong. The data was exactly right. But the smoothing process made it look totally different. And we can see this if you look up the northeastern United States. Everything from basically Indiana to the coast is the same population density. And we know that's not the case, right? We see that here, but only by choosing a very narrow Gaussian function. So we kind of come back to that same problem again. How do we choose our bin width or our smoothing function width to apply to high-dimensional data? And if you think this is hard in 2D, when you have like 1,000,000 dimensions, it gets way harder. The problem actually becomes exponentially more complex at that point. So, you know, the choice of trying to select this has been, there's literally volumes of books written on kernel density estimation just to figure out different rules of thumb for picking that width, and maybe sometimes it's wider than others, maybe it's adaptive, maybe it's predicted by something else, maybe there's, I don't know, cheese balls that give you the answer. The point is there a better way? And it turns out that actually there is a better way. Nature gives us a better way. And you know, the intuitive notion here is basically, wouldn't it be great if bins weren't shaped like cubes? Right? So if I'm in higher dimensional space, I don't need to think that everything is a big grid. Maybe there's a more natural shape that lends itself more appropriately to this problem of estimating density. Right? So by estimating density, we're estimating our normal, we're estimating our unusual. How can we do this better? It actually turns out that nature does this implicitly with bubbles. So the patterns of lines that you see here are actually something called the Voronoi tessellation. The Voronoi tessellation is the natural minimization. It's the region of, if I have a data point, and let's say it's a data point right here, and this is its Voronoi tessellation, that means that within this space outlined by this border, that is the closest point to whatever your input is. So if your input is here, that is the closest point, 100% of the time. And these are the boundaries where some other point becomes the closest point. So there could be another point here, here, and here, and so forth. Point is, the inverse of the area of these cells is your density of the cell. It's how unusual that region of space is. So in very dense areas of space where there's lots of people, as an example, your Voronoi cell is going to be tiny. Let's take a look here. So here's an example with using the coast of Finland, I think. Apologies if it's another country and someone beats me up for it. But basically, it shows you, it's very simple here. If I want to figure out what area has the least people in it, pretty easy to find. I just look for this, like what's the biggest cell? Well, the biggest cell is this one down here in the lower left corner, right? This huge offshore area where some person's living out on an island here. He's the only guy in that whole region. It seems kind of obvious, but the nice thing is this is really easily calculated as well. There's packages for this in C. It's called the QHull package. It's also implemented in Python and scikit-learn. And, this is great for finding individual points, but a cluster is a collection of points, right? So a bin, like our histogram, is not one individual point. So there's got to be some way to build off of this, some way to compose this, and we're going to go through this in a minute. Sure. So what you're seeing here, by the way, is if you were to take a line and draw a line between every point, and then take the lines perpendicular. So for example, if I take this one here, and I drew a line to that dot here, this border right here is perpendicular to that line and halfway in between. So it's the midpoint perpendicular line to every one of these other points when I do that comparison. That's sort of the implicit mathematical procedure that's generating the Voronoi tessellation. So let's take a look and see what this looks like. Now, I chose this one actually. This is from Jeff Scargill's work, the guy that did Bayesian blocks, and he said, okay, well, unfortunately, as a NASA scientist, we look at more than one-dimensional data, and I need to figure out a way to cluster this. This is the photon position data from a sky survey, okay? What's interesting about this is, does anyone want to take a guess at how many clusters are in this data? Take a guess. No, but I'm glad somebody said a high number. There's 23 clusters in this data. Totally not obvious. This is not something where a human's going to just walk up there. I mean, 3 of them are pretty obvious, right? But the other ones where the density is relatively consistent in the area and it can take an arbitrary shape for the cluster is not so obvious. Now, there's lots of clustering algorithms that if you were to apply them to this data right here would give you the answer. In fact, the irony of this is a lot of clustering algorithms actually require you to tell them how many clusters are in the data before they go and cluster the data. Think about that for a second, okay? That's like cheating. I know we have some college professors in here, so do you ever give your students the answer before the test? I mean, literally, that's what you're doing here. So what Scargill said was, let's start off with that data, and let's create the Voronoi tessellation. By the way, there's some really cool art that's done with Voronoi tessellations out there. You should check it out. Let's create the Voronoi tessellation. And does it tell us anything more than just the density of the individual regions? It does, in fact. It turns out that this actually tells us, it gives us a gradient as well. So it tells us what, if you think about the cells as being tilted in a certain direction, it tells us the tilt as well. We don't really know this directly, but it's calculated by these packages for us and makes life a lot simpler. And this actually indicates, it's 21, not 23. This actually indicates the number of clusters in the data and which nodes should be joined to other nodes. Now, the interesting problem is, this is just a heuristic. Okay, so if I go back to my tessellation, this gradient idea, this idea of kind of linking things on their path towards higher density, which is really what he's saying here, makes good sense, and it makes sense to us as humans, and it works on a lot of data, but it's not perfect. And the reason for this is that this is a global optimization problem, it turns out. So that means that basically I I can't just use local information around any individual point. I really need to use every piece of information every time I make an analysis for every point. And that gets really complicated, really hard, like really expensive, really quickly, and hard to apply to real-world problems. So we create these heuristics that kind of work well, but realize that you can always find some room for improvement in these methods. He's actually explored 2 or 3 different methods of this. The key here is, what's nice about this particular method is, again, it's a Bayesian method. He assumes a certain distribution within each of these cells, and the net result of that is we're incorporating our uncertainty in the diagram, in the clustering, and the clusters can be of arbitrary shape. So for example, the algorithm I told you about earlier that requires you to tell it the answer before you start, the only clusters that it can create are circular clusters. This is used very broadly. In fact, I will tell you that of all the machine learning libraries that I'm aware of for, quote, big data applications, the one thing that they will all have in them is that particular clustering algorithm. It's called k-means. Okay? So k-means is out there all over the place. There are all kinds of clusters in nature that are not round. Okay? So some folks have said, well, the obvious answer is let's just use lots and lots of clusters and make it really, like, we'll say there are 1,000 clusters in this data and let it figure it out from there. The moment you try and link up microclusters like this, you're right back to the heuristic problem again. Okay? You're right back to the same global optimization problem. So there's a lot of ways to kind of skin the cat. You can fake the Voronoi tessellation with k-means and then apply a similar aggregation method to build up a cluster and so on. But it's a little tricky, and you're going to have to spend some time with it. So we talked about patience. A lot of the methods we're showing you today can be used almost, I say almost blank sheet, like out of the box. You can just apply them. But they should still be checked by a human. That's that fusion of your domain experience. If you see clustering that doesn't make any damn sense, it doesn't make sense. Sometimes you'll get rare stuff, like here. This is a little unusual, especially that big sparse space, but it's an important point. Is there any questions on this stuff? Yeah. The gradient slide or this one? Like the Voronoi tessellation. Right. Yeah, it's you know, what's also interesting is if you look at I mean, you'll see standard lattices, but that's actually a spin glass structure too. Like you see that, and that's the microscopic structure of glass as well. I should say any non-uniform lattice is going to look almost like this. Yeah, that's why I'm saying nature abhors complexity and finds lowest energy solutions. The way that bubbles pop, merge, etc., that is a very natural form of energy minimization. Thanks, that's great. I'll have to see if I can find a microscopic picture of steel or something. Okay, so let's talk a little bit about time series. And you know, I guess at some level, time series is maybe the data that we all are most familiar with. In fact, it's a lot of people when they think of data science, they're thinking about applying it to time series, and then they start taking data science classes, and all they learn on is stationary, normal data, and then they go, how the hell do I analyze time series? Okay, so it's a little bit trickier than just looking at a standard data set. The reason why it's trickier is that when you look at a cross-sectional data set, like an Excel spreadsheet, you can look at all the points at once. Okay, so you have every single data point that's ever going to happen. They're assumed to happen effectively at the same time, or in a way that where the time doesn't matter in the measurement. And in order to convert a time series, that's like if you imagine a stock price, it's changing second by second by second. You have to think about how you're going to vectorize that, or how you're going to put it into. How do I convert that into a form that the typically predictive stationary models can use? So when you're modeling, you have kind of 2 options. You can either choose a stationary model, which is again 98% of the models that you'll learn, or a sequential model, a time series style model. Now you may say, well, it's time series. Why don't I just use time series? Like why would I bother using stationary stochastic models? The reason is that A, they're simple to use. B, you can get a lot of practical results out of simple stationary models, like simple linear models can provide good information about a lot of problems. And quite frankly, I think just the mathematics of sequential processes can be quite complicated. So they're not even well understood. We understand Gaussian processes where if you imagine a random walker, right? So I'm just kind of randomly taking a step. My step length as I walk around the room is effectively a fixed size. I'm just going to randomly turn and walk. We understand the dynamics of that. But as I was describing to him earlier, if I'm a Levy walker, or a Levy flyer, I think they're called, I may take random steps, and then I might suddenly teleport across the room to a different place. Estimating where I might be at any given time for that Levy process is much harder than that random walker process. So part of the challenge, obviously, it's kind of back to that sample problem discussion earlier, but part of the challenge is, how do I even know what the hell process I'm looking at? It's not like somebody tells you, oh, this is a Levy process. You know, what process governs the stock market? They don't know. Okay? If they knew, they would have modeled it by now. But they don't know. That's the point. And the process itself might be changing over time, too. So it might be Gaussian right now, it might be a random walker, and suddenly a hurricane happens, or there's 9/11, and now it's behaving like, you know, a Levy flight. So it's a completely different thing. So this is actually a great example. This is a heartbeat. Or is it? This is actually 8 hours of data. So it's not a heartbeat. This is seismic activity superimposed over an 8-hour time scale. So what's the challenge? Why would this matter? Why would I want to think about two different types of models here, stationary versus a dynamic model? The problem with the stationary model is I have to pick a window. I have to decide, like if I'm, like let's say I want to turn this into a high dimensional problem, right? I have one-dimensional data here. I've got some value that varies. And I say, okay, well, I can give it just the instantaneous value and tell it to predict the next value, but that probably isn't going to give me a good indication. So maybe I want to give it some context, right? What were the last 5 values, the last 10 values? Well, A, where do you stop? And realize that as you're escalating, as you add those points, you're increasing the dimensionality of your problem. So if I take the last 100 points, now my complexity in terms of the number of samples I need is very high compared to the simple case. So let me try and give an example. If this is 8 hours of duration, and I pick a window of, say, 10 minutes, I'm going to have all kinds of windows that are like this, just flat, nothing windows, right? And even the transition points are so relatively slow relative to the window, it's not going to capture the dynamics of the system, right? The dynamics of the system, the real dynamic that the human sees is there's this small activity, big spike, kind of a recovery, and then another period of stability. So 2 notes here. One, you can use a sequential model, which again have their own host of problems, or you can use a vectorized model, a stationary model. And this is where the human says, you know what, the relevant window size is this big. It's at least big enough to capture the largest feature that we can see in our data set that we care about. And that should be your primary rule of thumb. If you're stationarizing a data set, using those linear regression or other methods, you know, neural networks, whatever, you want to try and make sure that the window captures the feature that you really care about. And that can be tough. It's easy for this, but it's hard for things like English language, right? What's the right window size for English language text? Well, it kind of depends what the heck the context of the text is. You know, if it's tweets, you could probably get away with just looking inside the tweet. If it's a book, you might need information from the last paragraph, from the last chapter, etc. So the vectorization kind of represents a memory, like a working memory for your analysis. It doesn't have to be the exactly previous data either, right? Like at this point here, I could structure a vector that takes the previous value, takes the 10th previous value, takes the 100th previous value. I could do it with all kinds of different ways. There's all kinds of different ways to vectorize this, right? So when we said patience earlier, patience, part of that is parameterizations, dealing with these parameterizations. These window functions can be particularly tricky. So when you're looking at time series, the very essence of time series is wave analysis. So I know we have a lot of people that play around with audio, that do video editing. You're doing this all the time. You're using cool tools all the time that you could be applying to work. Things like a sine wave are very smooth and predictable, very easy to break down and analyze into their spectrum. Thanks. Some other waves are incredibly turbulent. They have hierarchical processes that induce turbulence, and they're not well understood. In fact, turbulence is one of the great unsolved problems in physics. It's one of the millennium problems. In fact, I think just recently, like last week or 2 weeks ago, they finally proved that the Navier-Stokes equations that define turbulence are incomplete. We thought they were complete for 80 years. Okay, they're not complete. And the reason why this is difficult, if you think about it, I mean, we just looked at one-dimensional time series. The wave, this is 2. Imagine 100 or 1,000 dimensions of wave analysis. It gets really complicated really quickly. There's no good way to model turbulence. You end up having to basically use optimization. So we have a bunch of tools that we can kind of use to look at time series. Probably the most frequent one, the one that most people are used to, is what they call spectral density analysis. It's basically the time series equivalent of clustering, but you're looking at frequencies. So I'm trying to basically break a time series down into a series of waves of different frequency. Big waves, real fast waves, etc. And you see this all the time in like audio processing and so forth. It's kind of the standard go-to method. And in particular, the Fourier transform is breaking down your input signal into a series of sine waves. Okay? The trick here is, and I should mention, by the way, it doesn't actually have to be sine waves. Okay? It can be random waves. They can be chaotic waves. There are complete other families that you can use to break things down. So if you go down this path of spectral analysis, there's a lot of interesting tools that you can apply here that can account for this. Another tool that we use, which is really involved in the comparison of time series. So like, let's say I want to compare 2 different time series. Imagine that you're vectorizing the motions of a person doing sign language, and you want to interpret that person's sign language over time. Well, if I take kind of the strict case, like every 1/10 of a second I'm going to take a photograph of that person and use that information, there's a sort of brittleness to that approach, right? I might move my hands faster or slower tomorrow. If I'm doing speech recognition, I might slow my tone of speech down. I might speed up really quickly. I could be, breathing helium and something weird's going on. The point is that just using like the Euclidean distance to compare points does not really give you a very good estimate of time. In fact, for speech analysis, it's basically useless. Instead, sort of the optimal way of doing this, at least the best way that anyone knows how at the moment, is called dynamic time warping, which sounds complicated, but it's not. It's basically just the Euclidean distance where we allow one of the time series to be squished and shifted in different ways so we can find sort of the best way that it could align if we really make it flexible. For things like speech recognition, this is the de facto gold standard, period. There's nothing as good as this. And for large volumes or for very large collections of time series, this is still the best method. It's a little expensive, though. It's a quadratic distance, like its complexity is quadratic. So you've got a pretty expensive distance function here. I should also mention that this is the this process of dynamic time warping. It's a neat little feature. It's the continuous numeric equivalent to the alignment of DNA sequences. So the sequence alignment problem with gaps for DNA is actually equivalent to time warping in the numeric domain, which is kind of neat. Now, there's 2 other kind of interesting little tools here that if you build off of dynamic time warping and you say, okay, well, what if I want to look for the most frequent patterns? What are the common patterns in my time series? Okay, what are the things that happen all the time? Those are called, a little bit of a different name from clusters, they're called motifs in the time series literature. By the way, the sort of lord of all things time series is a guy by the name of Eamon Keogh, and he teaches at UC Riverside, I think, or Davis. I was advising someone recently and basically said, look, that everything that you're trying to do with anomaly detection in time series is basically solved. This problem is basically well understood, extremely well understood in time series. Not the same in stationary data. So even if time series are super complex, we can basically create an anomaly detector and a classifier for time series with incredible accuracy using nothing more complex than just storing the time series as our database. Seems like, how could you do that? Don't you need some kind of deep neural network? No, you don't. I'll explain why in a second. The discord is the equivalent of an anomaly in a time series. So a discord basically is I'm not sure why he chose these words, by the way, but basically it's the most unusually shaped thing in your time series. Now what's interesting about his methods for motif and discord discovery is they line up really well with human intuition of where the unusual things are in time series. So if you take, for example, a heart specialist and he's looking at EKG output, he will notice subtle fluctuations and variations in that EKG output that are absolutely critical and indicative of something to him, and of course he can classify that. They may vary over their duration, okay? And it's almost always just the shape. So people are kind of shocked to find out that it's not really any more complicated than that. So here's an example of a tool that this is supposed to be a 4-hour class, by the way. If we had 4 hours, we would be spending time doing this and applying this. This is Explore CSV. If you hit me up after the show, I'll be happy to give you a copy of all the software. Basically, this particular package here takes time series. I believe these are from, I think this is actually from a bunch of sensor measurements. But basically, it's highlighting in red here all of the most unusual sections of the time series and how unusual they are. So the things that are kind of more deeply highlighted red, they're highly unusual. The things that are lighter red, they're not unusual. These are all the top 5% items here. In the second column, this column here, this is the power spectral density analysis of the same sets of time series. And then the final column here is what they call the linear autocorrelation, or basically repeats in linear time of patterns. Okay. Now we can see if we just look at the power spectrum, it's not exactly obvious. How do I find the unusual sections of the time series? Well, you might say, well, I'll just select out this, I'll remove these other frequencies, and then reverse the transform and see what pops up. It turns out that gives really bad results. Surprising. Because it's the combination of the frequencies at a specific time that yield specific patterns, and you don't get that captured here. So you're not destroying information with the PSD, but there's a whole bunch of complex domain information that's here that's not being displayed. Okay, so that is kind of lost. So how do we calculate motifs and discords? Well, basically, his analysis over, when I say that this guy's the Lord of Time Series, he has one paper out where he analyzes a trillion point time series. He has another one where he analyzes like a million billion point time series. All these like crazy synthetic data sets. And what he's found is that basically to find motifs, the common patterns, you use time warping. To find the discords, you use just the standard Euclidean distance. So you just take a window length, look for the Euclidean distance, you find the nearest neighbor of each section of the time series. So for example, I take this window here, and I compare it to every other window, except, and this is a very critical point because people do not do this, except any window that overlaps with me. This is not true for stationary data. If you compare it with any window that overlaps with you, you'll just get mud. But if you compare it to every other window that doesn't overlap with you, you'll get these nice clean results that show you exactly where the unusual things are. And interestingly enough, over extremely large collections of time series, even the dynamic time warping stuff for finding the motifs converges to the Euclidean distance. I mean, it's founded on Euclidean distance, so it's not that surprising. So it turns out that actually the vast majority of time series classification and prediction problems can be solved with a very simple technique called nearest neighbor classification, which is basically find the thing most similar to me, whatever its classification was, that's what I am. So if it was bad, I'm bad. If it's good, I'm good. There's some other modifications to that, like if my nearest neighbor is still really far away from me, then I'm probably not that thing, right? So there's, again, lots of variations on a theme, and we're going to get into these here in a second. So, getting a little short, I guess. Okay. So any questions on this stuff here? Okay. Is everybody doing okay? You need a break? You need a breather? Eamon Keogh, which is basically spelled E-A-M-M-O-N Keoghh. Might be Keogh. Yeah. Actually, it's funny. If you look up time, just look up time series data set, you'll find his name. He's probably that widely known. Okay. Any other questions? Okay. So, on that note, we're going to get into prediction analysis stuff. This is the hot model section of the show. So. Okay. So since we just talked about it, we're going to start off with k-nearest neighbors. And I personally think this is not where most people start their introduction to prediction, but it's definitely where I start my introduction to prediction. K-nearest neighbors are sort of the best known version of what are called lazy learners. Any idea? That's probably why I picked this picture, right? But basically, the idea is very simple. The idea is that we can predict the future based on stuff we already know, and we can use our best example, the things that are most similar to what we're seeing now, to tell us what the future should probably hold. Okay, so in that sense, it's almost the most intuitive way. There's been some interesting speculation recently that for all of the deep neural network and everything else research, that the human brain may actually just be k-nearest neighbors, but a giant database of k-nearest neighbors, continuous, right? This also kind of has another interesting thing, which is that if you take, there's a study recently by Andrew N., who's the chief data scientist at Baidu, and also the professor of a very popular series on machine learning at Stanford on YouTube. And he found that actually over a 10-year period, there's this kind of, because modeling is so sexy, and frankly because it raises money, there's a big focus in graduate computer science on new modeling methods, right? So everybody takes these old methods and they apply their new method, and they tweak one little parameter, and now it's a whole new method with a new name, and I'm so much better than you, and there's these very kind of competitive things. And what he said was, has there really been this steady improvement in these algorithms over the last 10 years? Because there's been a really strong march in improvement. And what he found out was when they actually compared the raw methods and applied them, he found out that actually no, the methods themselves were really no different from each other in this particular case. They just had more data and they had more compute time. So if you give linear regression more data, it will give you a better prediction. If you give k-nearest neighbors more data, it will give you a better prediction. So in that sense, a lot of models just get stronger the more data you have. Now, finding structure in complicated models is a different problem, and part of what makes stuff like deep learning interesting for those very big systems. But I've also seen, for example, very advanced variants of k-nearest neighbor that induce hierarchical structure, graph structures, et cetera, on top of this data that can perform just as well as deep learning networks, and they don't use a single neuron or black box optimizer or anything. It's notable that the one nearest neighbor, so k and the k nearest neighbor is the number of neighbors that you look at. It's notable that the one nearest neighbor graph is the Voronoi tessellation. Okay? So if I'm doing a simple k nearest neighbor classifier, and I'm looking at this data set, and I say, okay, what cluster does it belong to? When I find the nearest neighbor, it's just finding the tessellation and looking at the nearest neighbor and making that prediction. So the nice thing we use to find structure, to find our clusters and our outliers, we can directly use to find predictions and make predictions. Now, this particular model, obviously, is not a linear model. It's not a straight line, but it's a piecewise linear model. Remember all of our borders between our cells? They were straight lines. So there are really two kinds of models in general. There's linear models and nonlinear models. Basically, linear models trying to find the best straight line fit, and nonlinear models trying to find the best curved line fit. That's kind of a high-level way of thinking about it. And I'm going to let Alex cover linear models. Then we're going to bounce right back quickly and cover some other nonlinear stuff. So, thanks for your patience there. Oh, yeah. Oh. I'll just hold my head.
All right. Hopefully you can hear me better. All right, so we're going to go over basically linear regression. Has anyone ever used this before? All right, so we're going to start with a very simple example. We're going to look at a tip versus how much meal distribution. We look at this is basically showing us in the absence of any other data, this sample means that the best estimate of the future value. We're going to kind of get into this moving forward. Right now, the mean is the null hypothesis, meaning any predictive model has to be better than the mean to have any value. It is notable that the sample mean and is unbiased estimation. We're going to be going over some bias later on when we look at the PageRank, like what Google uses. And the means that the mean itself has a distribution. So with this, we look at it, we can kind of see the points are kind of distributed out based upon the actual tip amount for the meals. And we can see the average is, the mean here is 10. Now if we actually look at this and we look at the actual errors based upon it, we'll see that the sum of the squared errors is 120. We're going to remember 120 because we're going to go back to that once we actually get into the regression. So if we look and we just actually take it and we create a scatter plot where we take the tip amount and then the actual bill amount, we create this scatter plot. And we're basically going to be creating the linear regression for this. And you can kind of see here is where we'd be getting that mean line.
Just to add here, this is a little bit of exploratory data analysis stuff we talked about earlier. So the idea behind the scatter plot here is just see if linear makes any sense. Right? You could just apply it blindly, obviously, but here it has kind of an obvious relationship. It's kind of a line. So it's reasonable.
Yeah, and if you plot a scatter plot at something and it's like chaos on there, you probably wouldn't want to be using a linear model for that. So for this case, you can see that a linear model, there is a best fit line that we probably can't compute, which here, that's what we do. So step one is we have to find the centroid, which is the mean of each variable. And it will be one of the 2 points of the linear best fit line. So we can see in this, it's at a 7410, and like we said I was showing before, it kind of fits within this line here. All right, and now we're not going to really go into calculating this because we are kind of on time. So basically right now we just created that best fit line. So we find the slope of the line and then the change. So it should be known here that if this number is 0, you're going to get a negative value. And that means that you're not going to want to use this type of model for that. So this kind of lets you to see where that is. But yeah, if you have a x value that is 0, you're not going to want to use a linear regression for this.
Yeah, maybe the best lesson there is that the models do not apply infinitely over the entire domain, right? So you got, like, it's only applicable really when there's actually a bill. So you're not going to give back money to somebody that ate for free, as an example.
You usually don't tip when you just get water or something like that, if you're not charged for anything.
You have to use common sense to interpret models.
And then how do we know how good our model is? Well, basically we look at the residuals, or the actual, the square of the distance from prediction of our model to that, to the data points. So what that's really saying is, here was our actual data points. We kind of zoomed in on this. And here was that line. So if we look and see how close our line is to the actual data points, we can tell how accurate our data is. So let's say we had this, but all of our data points were all over the place. We had all these extra ones. We know that's really not a good method to use it, going back to that example. And then what we want to do now is actually calculate this type of error to see what it is. So for the first one, we looked at the tip amount based upon the meal amount. And then the second one that we just went over, the first one we looked over was the bottom one here, which was just tip amount. Then we looked at the actual tip amount versus the meal amount. And you can see that we have two different errors. So if we subtract those, we get like 80 and then 90 in some decimal places. 80 and some, and that will tell us how good our data model is. So you want to actually take both those points of reference, find the error, and then subtract those. And that gives us the sum of squared errors comparison, basically, which is the SSE value there.
It should be known that that's the method that Gauss created in 16.
Yeah, that was his least squares problem.
And, it's a pretty intuitive notion, too. Like, we have to use the central. We know we've got that one point that's going to be in our line. If I made, if our least fit line was the opposite direction entirely, down, it's going to be way off. So, for a linear model, it's such a nice, elegant thing. But that is the best linear model that you can construct, period. It's just directly solvable. You can do it cell, you can do it by hand. Lots of stuff.
You're getting at this. Yeah, we have
Okay, so we're going to talk about a pair of, in fact, I'll just cover graphs, if you don't mind. Yeah. We're going to cover a pair of nonlinear models. These are very commonly used. One important thing to recognize is that every nonlinear model has sort of data that it's good at and data it's not good at. And most nonlinear models can be massaged to be good at that kind of data it's not good at. Okay, so you should never really rule something out. Like, just because deep learning networks are new and cool and they say they have got that deep in them, doesn't mean that they're any good for your problem, and it doesn't mean that they're going to be easily applied to your problem. There's a lot of models, like for the last decade, support vector machines were the bee's knees. I mean, if you weren't using support vector machines, you were probably not going to get good results, or at least not results as good as people that were. So keep an open mind. So what is a support vector machine? You know, it kind of comes back to understanding how good a model can actually be, right? Why is one model necessarily better than another model? And is there a way to, you know, it's really easy in the linear case in a sense, but is there a way to sort of maximize goodness? So support vector machines have this idea that we want to try and separate what we call classes, or two different, say, sets of predictions. Predictions for A, predictions for, well, yeah, that's not good. Prediction for red and predictions for blue. We want to separate them by a hyperplane, by just a line in, say, two-dimensional space, or a plane in high-dimensional space. And we want to find the hyperplane that has what's called the maximum margin. So it's the hyperplane that has the most space between it and the example data points. So for example, we could choose B. B is not wrong. And if B was your model, you could classify red and blue, at least this data, just fine, right? But if a new point came in, say it was right here, it's going to be wrong. Okay, now it's going to be over here. By choosing A, we're kind of choosing a fattest road, if you will, between our different data sets. And basically it gives us a nice intuitive geometric understanding of, you know, there's a certain intuitive robustness to this model. Like we've got a nice margin of error within which we can still be within our model, and even for data we haven't seen yet, and everything is just dandy. These are also pretty easy to calculate. The other thing is that it doesn't have to be a hyperplane. So there's this great thing called the kernel trick, which basically lets us take a nice linear model, or sorry, a very nonlinear data set, like this one here. And even though this would be the maximal margin hyperplane, by using the kernel trick, we can basically project it over into a higher dimensional space, where we can then get a nice linear model to fit between them, and it's significantly easier to actually calculate that margin. And this lets us handle data sets that are significantly more complicated, for example, like this one. Okay, this is called the Swiss roll data set, and this is widely used. This breaks clustering algorithms, it breaks prediction algorithms all the time. It's kind of the, I don't say it's a gold standard, but it's like the entry-level model to, oh, you think you're a nonlinear model, and you can really find good margins, then you should be able to handle Swiss roll with no problem whatsoever. If you think about it, similarity and adjacency and so forth would be tough here. You know, if I use k nearest neighbor here, it's probably okay out here. You know, actually, it's probably okay in here where the points are really dense and there's a significant distance between it and the next points. But out here, the distance between each point in the class is almost the same as the distance between it and the next class. So k nearest neighbor actually gives very spurious, weird results on this kind of data. So support vector machines give you a way to kind of shortcut this process. I really do apologize. We have like 5 minutes. I'm going to try and fly through the remaining slides here. But another nonlinear model that's very popular are neural networks. And, you know, what are neural networks really? Neural networks are function approximation systems. That's one way to think about them. They're using a very simple piece of underlying function, in this case, the sigmoid function. And we're going to use this in combination. So we're going to use a linear combination of these things with different weights. And we're going to use that to estimate some crazy, wacky, nonlinear function. And it's interesting to note that this is the cumulative distribution function of the bell curve. Okay, this is also called the error function. There are other kinds of neurons. In fact, in deep learning, you might think, okay, well, this is pretty interesting. What about deep learning? What does it do? It doesn't even use a nonlinear neuron. It uses a linear neuron called a ReLU, a rectified linear unit, which actually is just flat and then an angled line. Okay, so you don't have to have really complicated component functions to create really complicated learning systems, which is maybe one of the important things to learn here. It's based on very simple building blocks, just applied in combination and in hierarchy. Basically, it is an optimization-driven approach. You typically wouldn't use ant colony optimization, but you literally could. It uses, most of the time, it uses a method called stochastic gradient descent, which is basically just following the curvature of our data, if you will, the manifold of our data, and trying to find something that minimizes it, or the valleys in our data. And it does that by calculating the derivatives and then using that information. So what is deep learning? Is deep learning just more of the same? Is it just layers of, like, 50 layers of neural network, or what? Well, it's a lot of things, really, but deep networks were actually developed in like 1968, and they used 9-layer deep neural networks then that seemed astonishingly sophisticated for their time. The breakthroughs that have happened in the last 10 years that you read about are really better ways to train neural networks, better ways to, simpler ways to represent those functions, and kind of the understanding that what a neural network is doing is creating a lossy compression of the data. And when you extrapolate that back, what you end up, when you look at a neural network and what it's doing, it's learning a hierarchy of features. So who's seen the stuff about Google and like Google Imagery learning cats? Cool, okay. So what it did there was it learned a series of stages. First, the first layer of our neural network in imagery learned edges. It learned that dark next to light next to dark indicates an edge in a picture. And it learned edges of different angles and orientations, okay? The next layer up in the neural network learned that features like corners are composed of multiple edges. And then corners, combinations of corners, can create, circles and squares and other things like that. And so as you apply more and more layers, you're taking this already lossy thing, like edges, and making something that has to be composed of edges, and making something that has to be composed of shapes, and making something that has to be composed, and eventually you get to cats, and human faces, and trees, and other things. And the reason why this is important is because a lot of structure in nature is self-similar. It occurs at many different scales. If you zoom way in on a fractal, it's exactly the same as if you zoom way out on the fractal. Now, nature's not that perfect, but it's similar enough that hierarchical representations are very important. And we see this all the time. Like if you write an outline for a paper, you can write the high level, there's an overview, and it's section 1, section 2, section 3, and it's going to cover these major points and whatever. That's a hierarchical representation. Okay, so that's all a neural network is doing. It's just learning the same thing. Okay, we're going to quickly touch on graph analysis as well. Graphs are really useful for analyzing structure and relationships between data. So interaction graphs are particularly important for security. And probably the most well-known, we're just going to cover two algorithms here. Probably the most well-known algorithm for graph analysis is something called PageRank. Basically, PageRank is looking at the popularity of pages or nodes in our graph based on the quality of the links that link to it and the number of links that link to it, right? So if you have a really high-quality site like your NBC.com or something and you link to my personal homepage, wow, I'm important. Okay? But if some junk site links to you, it's basically disregarded. You can actually apply this directly to security data, and our last slide actually has this, to find the most important, say, log lines in your log file, or the most important sequences of events. It's very easy to visualize and understand. So that kind of helps us understand, even though it's a link analysis algorithm, it's actually ranking the nodes in our graph. So our circles in the graph are what we're finding the measurements of. So what if we want to understand the paths? What are the most important paths through this data? The nicest way to do that is something called link salience. This turns out to be a really flexible way. There's literally hundreds of ways to analyze graphs. I'm not trying to say that these are the best or the only ones, but they're really practical for big security type tasks, mainly because they reduce the complexity of the representation down nicely. So link salience basically uses the shortest path algorithm that we all have networks powered by. And using Dijkstra's, it basically computes the shortest path from every node in our graph. So say this is our original graph. And for each node, it's going to find the shortest path for that node. It combines them all together, and the aggregate gives us a measure of the importance of each path. So the intuitive notion here is if a certain connection is the shortest path for a lot of nodes to other stuff, it's really critical. So an example of this is if you look at the World Travel Network as an example, the top one has the frequency of every single route flown by a plane over the course of a year. And that's kind of useful, but I mean, where do you start there? I mean, everything looks almost equally important. Same thing with the food web or the grams of carbon per year down the bottom, or the world trade thing down at the bottom. Oh, we skipped the graph. Darn. Oh man, that sucks. Okay, so basically if you use link salience to analyze this, what you end up with is it will reduce these graphs down to just a few critical hubs, the things that really are important. And what's astonishing is like for the air traffic, literally the salience rank is the world rank in the popularity of that airport. It just, they naturally align 1-to-1, which is the original experiment that kind of drove everyone nuts about this method. It can make a graph. You can basically then drop all the links with salience below a certain threshold and just look at the high salience links in your graph. And if you're looking at a big interaction graph, this will pull anomalies out like mad. Other thing too is if you take PageRank and you invert the weights, now you have an anomaly detection algorithm for your graph. So these two methods back to back paired up work really nicely. So here it is actually applied to a log file. This is just like a typical, this is from a Usenix conference, and it's basically about 25 million lines of a supercomputer log. first of all, how nice is that for 25 million lines of log? I mean, I can deal with that. Now, if I was not a total inept boob when it came to like building interactive UI, you could click it and drill into these different things and understand them. But the key is that the link weights are also linked by their salience. They're also colored by their salience. And notice that, like, why is this one so important? These nodes themselves are not that important in the page rank, but they're critical to the path. It turns out that's actually, that particular link, this bottom one, is actually the so-and-so logged in, or sorry, so-and-so authenticated, so-and-so has logged in. That kind of like standard sequence, like they've authenticated against this provider, such and such has logged in on this TTY. That sequence is so common in the log file that that's a critical path to looking at the log as a sequence of events. So again, it helps you understand very complicated data very quickly. And with that, we are done, I think, with 30 seconds to spare. So any questions for us? Oh man, that's got to be a miracle. Okay, thank goodness.
I like everything that you said.
Okay.
But then I look at catalog and just use like XG groups.
Sure, yeah.
Everything works out really well.
Yeah, Kaggle's convenient like that.
Right. So I guess what I'm asking is, like, why do you think that like some of these techniques like
Oh, TSNE is awesome, right? So like TSNE is a great example of a low-dimensional embedding, like I talked about earlier, especially for visualization. It's fantastic. Yeah, it's nice. I think they're all great, and literally what I don't want to do here is imply that these are the methods you should use for security, right? What I want to imply is get curious about these, and you're learning kind of the right things in terms of the path. They'll set you on the right path. So in the full day course, which there are 3 variants of this course, we cover TSNE, we cover the code, we actually get in some data. It's a matter of time. So, yeah. Yes. Oh, yeah, definitely, sure. Yeah, so this will go up online. DEF CON's asked it to do this in DEF CON 101 next year with a longer session.